Okay, so we're going to go in and finish our little bit of chapter 10 and then start on chapter 11. So what we were talking about last time is we were talking about the conformation of alkanes and how we know that because of electron repulsion, those carbons are all going to be in this kind of zigzag pattern. We call this the staggered form, rather than we call this the eclipsed, where you have kind of a U shape with that same number of carbon atoms. But we know that all these atoms have electrons and all electrons are the same charge. And so the electrons will repel each other. So they try to get as far away from each other as possible. And that results in a more staggered, stable conformation. So it's the stable conformation is designated as energetically more favorable. So you have less crowding. The same thing is true when you turn those alkanes into cycloalkanes. Still, the atoms still have electrons and they still want to get as far away from each other as possible. And so if you look at, we call this the chair and the boat conformation. The chair is kind of like the seat of a chair, whereas the boat kind of has an up and down. And so, like you could think of, the bow over here and the stern over here of a boat, right? That's kind of how it looks, but that's why they call it the boat and the chair. But the chair conformation allows the atoms to be farther apart. So the atoms themselves have more space, whereas here you would have more, basically they call it steric clashes, where the electrons and the atoms are getting too close and they really repel each other. So the boat conformation is much less stable than the chair conformation. Last section, there are only two reactions that alkanes can undergo. Alkanes are generally pretty unreactive, other than being oxidized. And oxidized is another way of saying burning in the presence of oxygen in a process that we call combustion. So this is what happens in your car every day when you drive it. You are combusting hydrocarbons in the form of gasoline in your car engine. The other one is called a halogenation reaction, where a halogen, and remember the halogens are the group 7A elements, right? So bromine, iodine, right? So on, so on, so on. Typically the most common are the chlorine and the bromine, but any of the halogens would work. So a halogenation is just a substitution reaction where you substitute a halogen for a hydrogen. And I'll show you what that looks like. So combustion, there are two forms of combustion. There is complete combustion, where you start with a hydrocarbon and you combust it in the presence of molecular oxygen, which is just a diatomic molecule where you have two oxygen atoms, and you produce carbon dioxide. So remember how to name things, right? We don't say monocarbon dioxide. The mono on the first element is understood. So we just say carbon dioxide. And you're also going to make water. And from that, you're going to generate heat energy, which is what drives your engine. You also have incomplete combustion. Incomplete combustion is very similar. You start with a hydrocarbon and you combust it in the presence of oxygen, but it doesn't go all the way to carbon dioxide. You end up making carbon monoxide. And this is why you should never be in your garage with your car running, because you can get carbon monoxide poisoning from the exhaust of your car. So your car is going to undergo both complete and incomplete combustion. It's also going to make water and heat energy. So that carbon monoxide is dangerous because it binds more tightly to the hemoglobin in your red blood cells than oxygen does. So it basically outcompetes all the oxygen for binding to your hemoglobin, and then your cells have nothing, no oxygen to breathe. All right, so the last reaction is halogenation. Halogenation, we said, was a type of substitution reaction where you have a replacement of, in this case, right? What are you replacing? You're replacing the hydrogen with a halogen, right? So what are you going to make in this reaction? And I'll show you one in a second. You're going to make an alkyl halide or a haloalkane. Either way, this kind of makes a little more sense with the naming convention that we've been using, but you have to have know both. And then a hydrogen halide. So all halogens, almost all halogens, will exist as diatomic. So you're not just going to see chlorine, you're going to see Cl2. You're not just going to see bromine, you're going to say Br2. So if you have some kind of a hydrocarbon, right, we'll do this. And we'll say this carbon has 3 hydrogens around it, and then this is the rest of the molecule. And it could be really long, could be really short. But one, because we have 2 bromines here, one bromine is going to replace the hydrogen. So the hydrogen is going to get kicked off, and you're going to end up with carbon, right? The R group, the hydrogen. And then what gets replaced? What gets put there? Well, a bromine. But how many bromines did we have? We had 2. So what do we have left? We have a bromine and a halogen. So both of those things are going to come together, and you're going to have HBr. So you are going to make a haloalkane. This is your haloalkane, and you're going to make a hydrogen halide. So this is really important because alkanes are generally unreactive, but if we can turn them into something different, then we can use them as starting materials to make lots of more complicated structures. So halogenation is kind of hard to get going, and so it needs a little help. And so it will only occur in the presence of either heat and or UV light. So let me show you some more examples here. So this is very similar to what I just showed you, where you have some kind of an alkane. So we know we have all carbon-carbon single bonds, and then we're adding it to a halogen. And so this halogen, we're representing it X2. So X could be a bromine or a chlorine, something like that, right? So if you substitute that in, that would be Br2 or Cl2, right? In this spot right there. So in the presence of heat or light, one of those, so what you actually have is, let's say you have bromine, one bromine atom bound to another bromine atom. And so one of those bromines is going to go in and replace a hydrogen, and then the hydrogen is going to come off and bind to the other bromine, so that you put one of the halogens on the hydrocarbon, and one of the halogens binds to the hydrogen that got kicked off. So you make your alkyl halide and your hydrogen halide. So here's an example with methane. Methane's our simplest, right? Well, only 1 carbon. And we're going to add it to bromine. And when we say that molecular bromine, that means 2 of them. And in the presence of heat or light, one of these bromines is going to go in and replace the hydrogen. And then that hydrogen is going to get kicked off, and that hydrogen is now going to bind to the other bromine atom. So you start with methane and bromine, and you react them together to make bromomethane. So all you're saying is you have a bromo group. You don't have to number it, right? Because there's only 1 carbon. And a hydrogen bromide. You can go more complicated, right? Ethane reacted with chlorine. The chlorine would go to any possible hydrogen. And in this case, it doesn't really matter which chlorine you put it on, carbon 1 or carbon 2. You don't really have carbon 1 or carbon 2. Either carbons could be 1, either carbon could be 2. So here you have the chlorine attaching to one of the carbons, right? And so you make chloroethane, and you would always give this carbon number 1 and this one number 2, because your chlorine's going to get the lowest number possible. Okay, and so it works no matter what kind of molecule you have. Let's say you even have a cyclohexane. Any of those carbons is replaced. Now, when you're drawing this in the homework, right, what you really would see on a line diagram is just this cyclohexane. And you would have to know where all the hydrogens are. And then if I react this with Cl2, what am I going to make? Really, all you actually have to draw is that same ring, and coming off of one of the carbons is a chlorine, right? I don't have to draw this hydrogen, and I don't have to draw the C, because those are understood in the diagrams. So just kind of be careful with that. We're just showing you the carbon here and here just for illustrating purposes. Okay, so that is the end of chapter 10, and we're going to go on to chapter 11.